October 12th, 1944. The Rhine River at Nijmegen. Oberst Friedrich Rabe stood on the eastern bank, his field glasses trained on the smoking ruins of the railway bridge his engineers had demolished just 36 hours earlier. The veteran Wehrmacht officer, commander of the 406th Infantry Division, allowed himself a thin smile. The British Second Army's advance had been stopped cold by the swirling grey waters of Europe's most formidable natural barrier. His staff intelligence officer approached with the morning reconnaissance report. "Herr Oberst, the British have reached the western bank in force. They're unloading equipment." Rabe lowered his glasses. "Let them unload. Without a bridge, they might as well be unloading on the moon." The Rhine is 400 metres wide here with a 6-knot current. It will take them weeks to establish a pontoon crossing under our fire, months to build anything permanent. By then, we'll have reinforced the entire sector. What Rabe didn't know, what German military doctrine hadn't prepared him for, was that British engineers were already assembling a bridge that would span his river barrier in less than 12 hours. A bridge that came in pieces small enough for a truck to carry but strong enough to support 40-ton tanks. A bridge so simple that infantry could assemble it under fire, yet so robust it could withstand artillery bombardment and keep functioning. The Germans had dismissed it as a toy when intelligence first reported its existence in North Africa. They called it the Kinderspielzeug, the children's plaything, mocking its simple panel construction and lightweight components. German engineering tradition favoured massive permanent structures, complex trusses, and heavy steel girders. The idea that a functional military bridge could be assembled from prefabricated parts like a child's construction set offended their sense of proper engineering. But by October 1944, that toy had already bridged hundreds of rivers, ravines, and obstacles across 3 continents. It had carried entire armies across barriers the Germans thought impassable. It had turned military geography on its head, making rivers into minor inconveniences rather than major defensive positions. And now it was coming to the Rhine. This is the story of the Bailey Bridge, the weapon that won the war without firing a shot. How British ingenuity defeated German engineering orthodoxy. How mass production overcame technical complexity. How a simple idea changed military logistics forever. And how German commanders stopped laughing when they discovered that destroying a bridge meant nothing if the enemy could build 2 more before dawn. The Bailey Bridge emerged from a very British combination of eccentricity and practical necessity. Its inventor, Donald Coleman Bailey, was a civil servant in the British War Office, a quiet, middle-aged engineer who had spent most of his career designing administrative buildings and reviewing construction contracts. He had no combat experience, no background in military engineering, and no formal training in bridge design. What he did have was a garden shed, a hobby of building model structures, and an obsessive personality that couldn't stop thinking about a problem. In 1936, Bailey had watched British Army engineers struggling with a demonstration of military bridging equipment at an exhibition. The bridges were complex assemblies of heavy steel components that required cranes, specialised tools, and highly trained personnel to erect. A simple 100-foot span took days to construct under ideal conditions. Under fire, it would be impossible. Bailey went home and started thinking. The problem, he realised, wasn't the strength or span of military bridges. British engineers knew perfectly well how to design bridges that could carry heavy loads. The problem was deployment. Every existing military bridge was essentially a miniature version of a permanent civilian bridge, built with the same engineering principles but using lighter materials. They required the same construction techniques, just compressed into military timeframes. This approach was fundamentally wrong. A military bridge wasn't a permanent structure. It only needed to last long enough to get an army across. It would be assembled under fire by soldiers, not peacetime construction crews. It needed to be foolproof because the people building it would be terrified, exhausted, and possibly under artillery bombardment. Every component had to be light enough for men to carry without machinery. Bailey's revolutionary insight was that a military bridge should be designed like furniture, not architecture. It should come in a limited number of standardized parts that could only fit together one way. It should require no special tools, no skilled labour, no time-consuming measurements or adjustments. It should be impossible to assemble incorrectly. In his garden shed in Sheffield, Bailey began building models using children's construction toys. He experimented with different panel configurations, testing how small identical sections could be connected to create longer spans. He discovered that by doubling or tripling panels vertically and horizontally, he could create bridges of vastly different load capacities using the same basic components. The breakthrough came in 1940 when Bailey realized that the main structural panel could be a simple rectangular frame of steel with a diagonal crossbrace. No complex trusses, no curved members, no specialized connections, just rectangles that could be pinned together. Each panel would be 10 feet long and weigh 600 pounds, light enough for 6 men to carry. By September 1940, Bailey had submitted his design to the War Office. The initial response was polite skepticism. Senior military engineers found the design almost insultingly simple. Real bridges didn't work like this. The panels were too light, the connections too crude. The whole concept violated established engineering principles. But Britain was desperate. The Dunkirk evacuation had cost the British Army most of its specialised equipment. Conventional military bridges had been abandoned in France. The army needed a bridging solution immediately, and there was no time to develop something conventional. Bailey was given permission to build a prototype. The first full-scale test occurred in December 1940 at the experimental bridging establishment in Christchurch. A team of Royal Engineers, none of whom had seen the design before, were given a pile of Bailey panels and told to bridge a 60-foot gap. They were provided with written instructions but no specialised training. The engineers were openly sceptical. One sergeant reportedly said, "This looks like something me kids would play with. How's it supposed to carry a tank?" 4 hours later, they had completed the bridge. A Churchill tank weighing 40 tons drove across without hesitation. The bridge didn't flex, didn't creak, didn't show any sign of stress. The engineers stood in stunned silence. The sergeant who had mocked the design walked across the bridge, jumped up and down in the centre of the span, and then did something unprecedented. He saluted the structure. "I don't understand how this works," he admitted, "but it bloody well does." What the sergeant didn't understand was that Bailey had accidentally recreated principles that nature had already perfected. The panel design mimicked the structure of honeycomb, using triangulated frames to distribute stress evenly across the entire structure. By allowing panels to be doubled or tripled, Bailey had created a modular system where strength could be added incrementally. A single panel bridge could carry light vehicles, double it vertically and it could carry medium tanks, triple it and it could support anything the army could field. The genius lay in the connections. Each panel had pins on one side and slots on the other. Panels could only connect one way. It was impossible to install them backward or upside down. The pins were tapered, meaning they would only seat fully when the panel was perfectly aligned. A soldier assembling a Bailey bridge in darkness or under fire couldn't make a mistake because the parts wouldn't fit together incorrectly. The British Army ordered 200 bridges immediately. By mid-1941, production had ramped up to 50 bridges per month. Each bridge came as a complete kit, everything needed packed in crates that could be loaded on standard trucks. A typical 120-foot single-span bridge required 24 panels, 48 transoms, 144 deck panels, plus pins, braces, and end posts. The entire kit weighed approximately 40 tons but could be transported by a single convoy. The instruction manual was 12 pages long. Most of it was diagrams. The first combat deployment came in North Africa in 1942. British 8th Army engineers used Bailey bridges to cross the numerous wadis, the dry riverbeds that became raging torrents during occasional rains. German and Italian forces had assumed these geological features would slow British advances, giving them time to prepare defensive positions. The Bailey Bridge changed that calculation completely. At Wadi Zigzao in Libya, German reconnaissance reported that British forces had reached the 200-foot wide gorge at dawn. The nearest conventional bridging equipment was 50 miles behind the British advance. The German commander, confident the British would be delayed at least 3 days, ordered his forces to consolidate positions 20 miles east. By noon, a Bailey Bridge spanned the wadi. By 1400 hours, British armour was across and advancing. The German positions were overrun before they could be properly fortified. German intelligence officers examining captured British engineering manuals were baffled by the Bailey Bridge specifications. The German translation described it as a transportable panel bridge system, but the concept made no sense in German engineering terms. Their military bridges were based on proven designs that had served the German army since the Great War. Heavy steel components, complex assembly procedures, specialized engineering units. The Bailey appeared to be a crude emergency measure, a stopgap that couldn't possibly perform as well as proper German bridges. Oberstleutnant Heinrich Kretschmer, a senior German military engineer, wrote in a 1942 technical assessment, "The British panel bridge represents interesting but ultimately flawed thinking. The standardized components limit optimization for specific crossing requirements. The simple pin connections cannot provide the structural integrity of proper welded or bolted joints. The light panels will prove inadequate under sustained heavy traffic. This is a design born of material shortage and desperation, not sound engineering principles. It may serve in the African theatre where crossing requirements are limited, but will prove inadequate in the demanding conditions of European warfare." The Germans were about to discover how catastrophically wrong this assessment was. The Sicily invasion in July 1943 provided the first large-scale demonstration of Bailey Bridge capabilities under intense combat conditions. The island's mountainous terrain was cut by deep gorges and seasonal rivers. Every road had multiple bridge points that German and Italian engineers had demolished during their retreat. Allied planners had anticipated that bridging delays would slow the advance, giving Axis forces time to establish defensive lines. What actually happened stunned both sides. American and British engineers working from opposite ends of the island began installing Bailey bridges at a rate that seemed impossible. Bridges appeared overnight. Spans that should have taken days were completed in hours. The advancing Allied armies never stopped moving. German commanders receiving reports of bridge construction speeds simply didn't believe them. General Major Eberhard Rott, commanding the 15th Panzer Grenadier Division in eastern Sicily, ordered his intelligence officer to verify a report that the British had bridged a 180-foot gorge near Lentini in under 8 hours. "This is clearly an error," Rott insisted. "Perhaps 8 days, misreported as 8 hours. No bridge of that span can be constructed in less than a week, even by the best engineers under ideal conditions. The British are good engineers, but they cannot violate the laws of physics." The intelligence officer returned with photographs taken by Italian civilians. The bridge was real, fully functional, and had been carrying Sherman tanks within 10 hours of the engineers arriving on site. Rott studied the photographs in silence. Finally he spoke. "If the British can build bridges this quickly, our entire defensive doctrine is obsolete. Every river, every gorge we've counted on as a natural defensive barrier is meaningless. They can bridge anything faster than we can fall back and prepare new positions." He was exactly right. The Bailey Bridge was rewriting the fundamental rules of military logistics and defensive strategy. By the time Allied forces reached the Italian mainland in September 1943, the Bailey had evolved from an interesting innovation to an essential weapon. The Italian campaign would prove to be the ultimate test, a nightmare of mountains, rivers, and deliberate German demolitions. Italy's geography seemed designed to favour the defender. Rivers flowed perpendicular to the Allied axis of advance, forcing multiple crossings. Mountain roads clung to cliffsides with bridges spanning deep gorges. German engineers, masters of defensive warfare, had prepared the peninsula for a fighting retreat, identifying every bridge, every crossing point, every choke point. As they withdrew, German demolition teams systematically destroyed Italy's infrastructure. Not just bridges, but approach roads, retaining walls, anything that would complicate Allied engineering efforts. They did their work thoroughly and expertly. Bridges didn't just fall. They were cut with precision charges at critical stress points, ensuring maximum damage with minimum explosive. The German plan was sound. Force the Allies to rebuild Italy's transportation infrastructure while advancing through mountains against prepared defences. Each river would cost days or weeks of delay. The Apennine mountain range running down Italy's spine would become a fortress. But the plan hadn't accounted for the Bailey Bridge's capabilities. At the Volturno River in October 1943, German engineers had demolished a beautiful medieval stone arch bridge, dropping thousands of tons of masonry into the riverbed to complicate any crossing attempt. The German defensive line was established on high ground 3 miles north of the river, positioned to dominate any bridging attempt. The sector commander, Oberst Otto von Schell, was a veteran of the Eastern Front where river crossings had proven extraordinarily costly for attacking forces. Von Schell positioned his artillery to cover the destroyed bridge site and the two most likely alternative crossing points. His forward observers had range cards prepared for every square metre of the riverbank. Any British engineering effort would be met with immediate devastating fire. On the night of October 12th, British engineers began assembling a Bailey bridge 400 yards downstream from the demolished stone bridge, working in darkness with minimal lighting. German artillery, firing on pre-registered coordinates, began falling within 20 minutes. Engineers were killed and wounded, panels were damaged, the approach road was cratered. Von Schell, monitoring reports from his command post, was satisfied. The British were attempting a crossing in a terrible location, under fire in darkness. Even with their fast assembly bridge, they'd need at least 36 hours to complete the span. His reserves would counterattack at dawn, destroying any partial bridge structure. At 05:30 hours, von Schell received a radio report that made no sense. The British bridge was complete and tanks were crossing. He demanded confirmation, assuming the report was garbled. Confirmation came with the sound of Sherman tanks advancing up the road toward his positions. The British had completed a 180-foot Bailey bridge under continuous artillery fire in less than 7 hours. Von Schell ordered an immediate withdrawal, recognizing that his defensive line was already compromised. In his later report he wrote, "The British possess a bridge that can be erected under combat conditions faster than we can mass sufficient combat power to prevent crossing operations. Standard defensive doctrine assumes attackers will require 24 to 48 hours to bridge major obstacles, allowing adequate time for reinforcement and counterattack preparation. This assumption is no longer valid. British engineering capabilities have compressed timelines to the point where river barriers provide only minimal delay. New defensive doctrine is urgently needed." The problem for the Germans was that no defensive doctrine could counter the Bailey Bridge's fundamental advantage. It wasn't just fast to build, it was fast to rebuild. Damaged sections could be replaced in minutes. Destroyed spans could be reconstructed in hours. The bridge's modular nature meant that any damage short of complete destruction could be rapidly repaired. At the Garigliano River in January 1944, German artillery managed to knock out the centre section of a Bailey bridge supporting the British advance. The German forward observer who called in the successful strike reported the bridge destroyed, expecting congratulations. He received orders to maintain observation instead. Within 90 minutes, British engineers had replaced the damaged section. The bridge was back in service before German infantry could organise a counterattack to exploit the temporary break in Allied logistics. The observer reported this impossible development to his battery commander, who didn't believe it. The battery commander reported to division headquarters, who demanded photographic evidence. By the time the photographs were developed and distributed, the British had advanced 5 miles beyond the crossing. German engineer officers studying these reports began to understand the horrifying reality. The British hadn't just designed a fast bridge, they'd designed a bridge that was essentially indestructible through conventional means. Destroying it required hitting it with artillery or bombs, but unless you completely obliterated the crossing site, British engineers would simply rebuild it using replacement panels from their abundant stockpiles. Generalleutnant Fridolin von Senger und Ettelin, commander of Justitian's Panzer Corps defending the Gustav Line, wrote in his diary in February 1944, "The British Bailey Bridge represents a revolution in military engineering that we failed to recognise until too late. Our doctrine treats bridges as critical, vulnerable infrastructure to be destroyed and denied. The British treat bridges as consumable supplies to be used and replaced as needed. They have industrialised bridge building the way we industrialised armour warfare. Our engineers are craftsmen building custom solutions for each obstacle. Their engineers are factory workers assembling standardised products. In warfare, the factory approach wins." The numbers bore out von Senger's assessment. By early 1944, the Allies had erected over 3,000 Bailey bridges in the Mediterranean theatre alone. They were losing bridges to German fire and demolitions regularly, sometimes dozens per week. It didn't matter. Production had ramped up to the point where Bailey bridges were arriving in Italy faster than they could be installed. Supply depots held thousands of panels, enough to bridge every river in Italy twice over. The standard British engineer company carried enough panels to bridge a 200-foot gap with capacity for 40-ton vehicles. If they needed more capacity or longer spans, trucks would deliver additional panels within hours. The Germans had nothing comparable. Their military bridges were still based on complex designs, requiring specialized components and trained personnel. At the Rapido River, German engineers watched through binoculars as British forces installed a Bailey Bridge in a single night. A German engineering officer requested permission to examine the bridge after its eventual capture. His request was denied because the British positions never retreated far enough for the Germans to reach the structure. The Anzio landings in January 1944 demonstrated another Bailey Bridge capability that German planners hadn't anticipated. The Allies brought disassembled Bailey Bridges ashore in the initial landing, along with the infantry and armour. Within 48 hours of the landing, Bailey Bridges were spanning drainage ditches and small streams throughout the beachhead, ensuring armour could move rapidly to counter German attacks. This wasn't how amphibious. Assaults were supposed to work. Standard doctrine called for securing the beachhead first, then bringing engineering equipment ashore, then beginning infrastructure construction. The Bailey Bridge was light enough and simple enough to be combat-loaded with frontline units, bringing engineering capability ashore with the assault waves. German counterattacks at Anzio repeatedly found that terrain they expected to be impassable to Allied armour had been bridged. Small streams that should have channelized Allied movement had Bailey spans across them. Positions that should have been secure behind natural obstacles were suddenly accessible to Sherman tanks. The psychological impact on German commanders was significant. They were fighting an enemy who could reshape the battlefield's geography to suit their needs, while German forces were increasingly constrained by demolished infrastructure they couldn't repair. By the spring of 1944, as Allied forces prepared for the Normandy invasion, the Bailey Bridge had proven itself across every conceivable environment and condition. In Burma, British and Indian forces used Bailey Bridges to cross jungle rivers during the monsoon season, building spans over raging floodwaters that shifted daily. In the Pacific, American engineers, who had adopted the Bailey design enthusiastically, bridged ravines and rivers on Pacific islands, often working while Japanese snipers fired at them from the surrounding jungle. The design had been refined through combat experience. Engineers developed techniques for rapid assembly, including rolling Bailey bridges out over rivers using improvised launching equipment. They learned to pre-assemble sections behind cover and then push complete spans into position in minutes rather than hours. They developed armoured shields that could be attached to panels, allowing construction under direct fire. But the ultimate test was coming. The Normandy invasion would require crossing the largest number of obstacles in the shortest possible time while advancing through defended terrain. Every stream, every crater, every demolished bridge would need to be crossed immediately to maintain momentum. The Bailey Bridge would need to perform flawlessly, because the entire invasion timeline depended on maintaining rapid advance rates. German commanders in France knew the Allies were coming. They knew about the Bailey Bridge and its capabilities. They'd received reports from Italy describing the bridge's performance. Some officers advocated for developing German equivalents, but the resources and industrial capacity weren't available. Others suggested that the best defence was to destroy everything so thoroughly that even the Bailey Bridge couldn't span the obstacles. Feldmarschall Erwin Rommel, inspecting Atlantic Wall defences in May 1944, understood the problem perfectly. He'd faced Bailey Bridges in North Africa and knew what was coming. The British bridge, he told his staff, means we cannot rely on static defences behind rivers and obstacles. They will bridge any gap we create within hours. Our defence must be mobile and in depth, forcing them to fight for ground rather than simply bridging obstacles. Every bridge site must be covered by direct fire weapons that can engage their engineers during construction. Destroying the bridge after completion is pointless. We must prevent completion. Rommel's insight was correct, but implementing it proved impossible. The Normandy bocage terrain didn't allow for the mobile defence he envisioned. The small fields and high hedgerows channelized German units as much as Allied forces, and there were simply too many potential crossing sites to cover them all adequately. On June 6, 1944, the first Bailey Bridge panels came ashore on Omaha Beach before the beachhead was fully secured. By June 7th, engineers were installing bridges over cratered sections of the coastal road. By June 10th, Bailey Bridges were spanning obstacles throughout the beachhead, creating a logistics network that kept supplies flowing to advancing forces. The Germans fought ferociously, but they couldn't stop the bridges. Every blown culvert, every cratered road, every demolished stream crossing was bypassed or spanned within hours. Panzer units attempting to exploit gaps in Allied lines found themselves attacking across Bailey bridges that shouldn't have existed, facing Allied armour that shouldn't have been able to reach those positions. At the Weser River, a key German defensive position, American engineers came under intense artillery and mortar fire while installing a Bailey bridge. The German defenders assumed the bridging attempt would be abandoned, as conventional military doctrine suggested that engineering operations couldn't continue under such heavy fire. Instead, the American engineers kept working. Men were killed and wounded, panels were damaged, but more engineers moved forward and the assembly continued. The bridge was completed under fire, and American armour crossed immediately, overwhelming the German positions before reinforcements could arrive. German after-action reports from Normandy repeatedly mention the Allied bridging speed as a critical factor in defensive failures. Oberst Kurt von Ribbentrop, commanding a defensive sector near St. Lo, wrote, "Allied engineering capability exceeds our capacity to create obstacles. We demolish a bridge, they span it overnight. We crater a road, they bridge the crater. We flood low ground, they build roads over the water. Every advantage we create through demolition is temporary, lasting perhaps 12 hours at most. This is insufficient time to prepare alternate defensive positions or withdraw supplies. The effect is that we are fighting a mobile offensive battle while attempting to conduct a defensive campaign." The breakout from Normandy in late July 1944 demonstrated how completely the Bailey Bridge had changed operational warfare. General George Patton's Third Army, racing us across France, was supported by engineer units that kept pace with the armour. Bailey bridges appeared along Patton's supply routes as fast as the army could advance, spanning streams and craters that should have slowed the American juggernaut. Patton, not known for praising engineers, told reporters, "My men can fight anywhere they can get to, and these bridge builders make sure they can get anywhere." The German army, falling back toward the Rhine, attempted to implement Rommel's doctrine of destroying infrastructure so thoroughly that reconstruction would be impossible. They dropped railway bridges into rivers, destroyed lock systems on canals, cratered road junctions with massive demolitions. The scorched earth policy was implemented with German efficiency and thoroughness. It delayed the Allies by approximately 36 hours. French and Belgian civilians, watching German demolition teams destroy every bridge in their towns and villages, were devastated. These bridges, some hundreds of years old, represented vital infrastructure that would take years to rebuild. Within days, they watched Allied engineers install Bailey bridges at the same sites, creating functional crossings that carried more traffic than the original structures. At Maastricht in September 1944, where the Germans had demolished all 12 bridges across the Maas River, British engineers installed 14 Bailey bridges within 1 week. The German demolitions had cost months of preparation and thousands of pounds of explosives. The British reconstruction took one engineer brigade less time than it took German forces to fall back to their next defensive line. This asymmetry, the time required to destroy versus the time required to rebuild, became a critical factor in the war's final phase. German commanders realized they were expending significant resources on demolitions that provided minimal delay, but they had no alternative. Leaving bridges intact would allow even faster Allied advances, so they kept destroying infrastructure, knowing it was largely futile, because not destroying it was even worse. The Battle of the Bulge in December 1944 provided an unexpected demonstration of the Bailey Bridge's versatility. When German forces broke through American lines in the Ardennes, one of their objectives was to destroy Bailey bridges in the American rear areas, disrupting logistics and trapping forward units. German commandos and paratroopers specifically targeted bridges for demolition. They succeeded in destroying several Bailey spans. American engineers rebuilt them before the German advance could exploit the gaps. The speed of reconstruction was so rapid that German forces found themselves attacking positions that, according to their intelligence, should have been isolated behind destroyed bridges. Instead, American reinforcements and supplies were flowing freely across replacement Bailey bridges installed in the middle of a battle. Oberst Otto Skorzeny, commanding German Special Forces, during the Bulge had been briefed that destroying American bridges would cause logistical collapse. After the battle, he reportedly said, "We destroyed perhaps 20 of their bridges. They rebuilt them all within 2 days. We wasted elite troops on missions that accomplished nothing because the Americans treat bridges like ammunition, expendable and easily replaced. This is not a military advantage. It is an industrial revolution in engineering." As Allied forces closed on the Rhine in early 1945, German commanders knew the final defensive barrier was approaching. The Rhine, nearly 1,500 feet wide in places with strong currents and deep water, was Europe's greatest natural obstacle. Every bridge had been prepared for demolition. Emergency destruction charges were installed, guards were posted, backup detonation systems were prepared. Surely the Rhine would provide the time needed to organize final defenses. The capture of the Ludendorff Bridge at Remagen on March 7, 1945, provided the first Allied bridgehead across the Rhine. German efforts to destroy the bridge partially succeeded, but Americans held the damaged structure long enough to establish a crossing. The question became whether they could expand and reinforce the bridgehead before German counterattacks eliminated it. Bailey bridges provided the answer. Within 24 hours of capturing Remagen, American engineers began installing Bailey bridges alongside the damaged Ludendorff span. Working under German artillery fire, including experimental V-2 rockets, specifically targeted at the crossing site, engineers completed multiple Bailey spans. When the damaged Ludendorff bridge finally collapsed on March 17th, it didn't matter. 4 Bailey bridges were already carrying traffic, with 2 more under construction. German commanders watching from the eastern bank realized the final barrier had fallen. General Oberst Alfred Jodl, Chief of Operations for the German High Command, stated at a situation conference, "The Rhine has been bridged by the enemy using temporary structures installed faster than we can destroy them. The barrier we have relied upon for our final defense has proven meaningless. If we cannot hold the Rhine, we cannot hold anywhere." The Rhine crossings in March 1945 involved dozens of Bailey bridges installed at multiple points along the river. British forces crossing at Wesel used Bailey bridges to create a logistics network, supporting the largest airborne operation since Normandy. American forces crossing at Mainz, Worms, and other points each installed multiple Bailey spans. In total, over 100 Bailey bridges crossed the Rhine within 3 weeks of the first crossing, carrying the weight of an entire army group. German attempts to destroy these bridges through air attack, artillery, and commando raids failed consistently. The bridges were either too well defended to reach, or, when damaged, were repaired faster than the Germans could organize follow-up attacks. The final irony came in. The war's last weeks when advancing Allied units discovered German engineers attempting to construct their own version of the Bailey Bridge. Desperate for a solution to their own demolished infrastructure, German engineers had reverse-engineered Bailey panels and were producing small numbers at scattered facilities. The German version was heavier, more complex, and required more skilled assembly. It was, in other words, a perfect example of German engineering excellence making something simple into something complicated. One captured German engineer officer, when asked why the German military hadn't adopted the Bailey design earlier, explained, "We examined captured bridges in 1942. Our engineers concluded the design was adequate for the British, but unsuitable for German precision standards. We believed we could develop a superior system incorporating our engineering expertise. By the time we realized the British design was actually superior specifically because of its simplicity, we lacked the industrial capacity to produce it in meaningful numbers." The final statistics of Bailey Bridge deployment during World War II revealed the scale of the achievement. Over 700 million feet of bridging, enough to span the Atlantic Ocean 20 times. More than 200 different bridge types, from simple 30-foot spans to complex 1,400-foot structures carrying the heaviest tanks. Bridges installed on every continent where fighting occurred, in every climate from Arctic Norway to tropical Burma, in mountains and jungles and deserts. The longest Bailey Bridge span constructed during the war was 154 feet, over the Chindwin River in Burma, a structure that would have been considered a major engineering project in peacetime. It was installed by British engineers in 6 weeks using local labour, with the panels delivered by truck over mountain roads barely adequate for ox carts. The Germans, had they needed to bridge the same obstacle, would have required months and specialised equipment they no longer possessed. Perhaps the most telling assessment came from Albert Speer, Nazi Germany's Minister of Armaments, in his post-war memoirs. Speer had overseen German industrial production and understood the relationship between industrial capacity and military effectiveness. The Bailey Bridge, he wrote, represented Allied industrial and engineering philosophy perfectly. It was not the most elegant solution, not the most technically sophisticated design, not the approach German engineers would have taken. but it worked reliably under all conditions, could be produced in enormous quantities, and could be employed by minimally trained personnel. It won not because it was the best bridge in an engineering sense, but because it was the best bridge in a military-industrial sense. We Germans never understood that distinction. We kept trying to produce perfect solutions when adequate solutions deployed in overwhelming numbers would have served better. The British Bailey Bridge should have taught us this lesson in 1942. By the time we learned it, we had lost the war. After the war, the Bailey Bridge became the standard military bridge for armies worldwide. American forces adopted it completely, designating it the M2 Bailey Bridge. Soviet forces, having captured examples in Germany, reverse-engineered it and produced their own version. Nations emerging from colonial rule adopted the Bailey design because it could be manufactured with limited industrial infrastructure. The design proved equally valuable in peacetime. The simple, robust construction made Bailey bridges ideal for emergency infrastructure replacement after natural disasters. Floods, earthquakes, typhoons, situations where conventional bridge construction would take months, could be addressed with Bailey bridges installed in days. By the 1960s, Bailey bridges were being used on every continent for both military and civilian applications. Rural roads in developing countries were opened using Bailey spans. Disaster relief organizations maintained stockpiles of Bailey panels for emergency deployment. The design had transcended its military origins to become a fundamental tool for civil engineering. Donald Bailey, the quiet civil servant who invented the bridge in his garden shed, received a knighthood in 1946 for his contribution to the war effort. He returned to his civilian career, designing administrative buildings and reviewing construction contracts. He rarely gave interviews and never sought recognition. When asked about his bridge, he typically said it was just an obvious solution to a straightforward problem, as if designing something that changed military history was a minor achievement. General Dwight Eisenhower, Supreme Allied Commander in Europe, had a different assessment. In his post-war memoir, Eisenhower listed the Bailey Bridge as one of the three most important technological developments of the war, alongside radar and the atomic bomb. The Bailey Bridge, Eisenhower wrote, was the single most important piece of engineering equipment used in the European theatre. Without it, our advance from Normandy to the Rhine would have been impossible. Every time I saw a Bailey Bridge, I knew we were going to win because I was seeing proof that our industrial capacity and innovative thinking could solve problems faster than the enemy could create them. General George Marshall, Army Chief of Staff, stated, "Wars are won by logistics, and logistics depends on transportation. The Bailey Bridge kept our transportation network functioning despite everything the enemy did to destroy it. It was worth its weight in gold, and we deployed millions of tons of it." Soviet Marshal Georgy Zhukov, after examining Bailey bridges during the Allied advance, reportedly told his staff, "This is why we are allied with Britain and America. They think of these things, simple, practical solutions to complicated problems. We must learn this approach." The Germans, in their post-war military analysis, returned repeatedly to the Bailey Bridge as an example of where their engineering culture had failed them. German military engineering had been superb in many ways, but it had been oriented toward complexity, specialization, and technical excellence. The Bailey Bridge represented the opposite philosophy and had proven superior under combat conditions. In 1947, the US Army published a comprehensive study of combat engineering in World War II. The section on bridging concluded, the Bailey Bridge provided Allied forces with a decisive advantage in operational mobility. German forces, unable to match our bridging speed, fought at a constant disadvantage in mobile operations. The ability to cross obstacles immediately allowed continuous pressure on retreating German forces, preventing them from establishing stable defensive lines. This maintained operational tempo was a direct result of superior engineering equipment, specifically the Bailey Bridge. The study noted that German forces had possessed excellent engineers and sophisticated demolition techniques. What they lacked was a bridge that could be deployed fast enough to neutralize those demolitions. The result was that every river, every gorge, every obstacle the Germans created was temporary, while every Bailey Bridge the Allies built was effectively permanent until they chose to remove it. Modern military bridges still use Bailey's core concepts: modular construction, standardized panels, simple connections that work one way, designs that can be assembled without special tools or training. The specific Bailey design has been superseded by newer systems, but the fundamental philosophy remains unchanged. In remote areas of the world, original Bailey bridges from World War II are still in use. In India, Burma, and parts of Africa, Bailey spans installed by Allied engineers in the 1940s still carry traffic. Some have been in continuous use for over 75 years, supporting loads far beyond their original design specifications. These bridges were meant to be temporary, used for weeks or months and then removed. The fact that many have served for decades testifies to how well Bailey understood the fundamentals of structural engineering. At the Imperial War Museum in London, a complete Bailey Bridge section is displayed with an explanation of its significance. Visitors can see the elegant simplicity of the design, the rectangular panels with their diagonal bracing, the pins that connect them. Most visitors don't initially understand what they're looking at. It seems too simple to be historically significant. But the museum placard quotes Lord Beaverbrook, British Minister of Supply during the war. The Bailey Bridge was the best and most useful invention of the war. Without it, we could not have won. In 1985, during a reunion of British and German military engineers, a German veteran officer approached Donald Bailey, then in his 80s. The German had served in Italy and remembered watching Bailey bridges appear overnight, replacing crossings his unit had demolished with great effort. "I hated your bridge," the German told Bailey. "We would work for hours to destroy an important crossing, knowing we had delayed the British advance by at least a week. The next morning your bridge would be there and tanks would be crossing. It was demoralizing. We felt like everything we did was meaningless." Bailey reportedly replied, "That was rather the point." The German veteran nodded slowly. "We kept telling ourselves it was a crude temporary structure, inferior to proper German bridges. We wrote reports explaining why our engineering approach was technically superior. But your crude bridge won the war while our superior engineering lost it. That was a hard lesson." This exchange captured the essential truth about the Bailey Bridge. It wasn't the most elegant solution, or the most technically sophisticated design. German engineers could have designed something more complex, more optimized for specific conditions, more representative of engineering excellence. But they would have designed something that required specialized manufacturing, skilled assembly, and careful maintenance. They would have created a masterpiece that couldn't be mass-produced or rapidly deployed. Bailey created something that worked. Not perfectly, not elegantly, but reliably and repeatedly under the worst possible conditions. It was engineering in service of practical objectives rather than technical perfection. This pragmatic approach offended German engineering sensibilities, but it won battles and ultimately the war. The post-war industrial world learned this lesson broadly. Japanese manufacturing in the 1950s and 60s adopted similar principles, focusing on reliability and mass production over individual excellence. American industrial design shifted toward modular construction and standardized components. The Bailey Bridge became a case study in business schools and engineering programs, an example of how simple solutions to complex problems often outperform complex solutions. In military academies worldwide, the Bailey Bridge is taught as an example of how industrial capacity translates to combat power. The bridge itself was a weapon, not in the traditional sense of destroying enemy forces, but in enabling friendly forces to move faster than the enemy could react. This represented a new category of military capability, where logistics technology provided decisive battlefield advantage. The psychological impact on German commanders during the war cannot be overstated. These were men trained in military doctrine that treated natural obstacles as significant defensive positions. Rivers were barriers that would delay enemy advances for days or weeks. Gorges and ravines would channel enemy movement into predictable patterns. Destroyed infrastructure would force enemies to pause, consolidate, and rebuild before continuing operations. The Bailey Bridge invalidated all of these assumptions simultaneously. Rivers became minor inconveniences, gorges were spanned overnight, destroyed infrastructure was replaced faster than it could be demolished. German defensive planning, which relied heavily on exploiting terrain and obstacles, collapsed when obstacles ceased to function as barriers. Oberst Hans Speidel, who served as Rommel's chief of staff in France, wrote in his post-war analysis, "We prepared elaborate defensive schemes based on the assumption that certain terrain features were impassable or would require significant time to cross. These assumptions were reasonable based on historical precedent and our understanding of enemy engineering capabilities. The Bailey Bridge destroyed these assumptions. We found ourselves defending positions that enemy armour could reach within hours of encountering obstacles we believed would provide days of security. The psychological effect was severe. Commanders lost confidence in their defensive positions because they had lost faith in the terrain itself. This psychological dimension extended beyond individual commanders to the entire German military structure. By late 1944, German forces were in constant retreat, falling back from one defensive line to another. Standard doctrine called for demolishing infrastructure during retreats to delay pursuit. But German engineers performing these demolitions knew they were accomplishing almost nothing. The bridges they destroyed would be replaced within hours. The roads they cratered would be spanned by morning. The sense of futility this created undermined morale throughout German engineering units. These were skilled soldiers performing dangerous work, often under fire, knowing their efforts would prove essentially meaningless. Some units began performing perfunctory demolitions, placing charges but not optimizing destruction, understanding that thorough demolition and hasty demolition achieved identical results when facing an enemy with unlimited Bailey bridges. In contrast, Allied engineers developed tremendous pride and esprit de corps around their bridging capabilities. British and American engineer units competed informally to see who could install Bailey bridges fastest. Records were set and broken repeatedly. The 291st Combat Engineer Battalion achieved a record time of 6 hours and 20 minutes for a complete 180-foot double-double Bailey bridge, a structure capable of carrying the heaviest Allied tanks, assembled under blackout conditions. This competitive spirit drove continuous improvement in assembly techniques. Engineers developed specialized tools, not required by the design, but helpful for faster construction. They created assembly line methods where teams specialized in specific tasks: panel placement, pin insertion, decking installation, allowing them to work with factory efficiency even in combat zones. They invented launching systems using rollers and counterweights to push assembled bridges across gaps rather than building them span by span. The innovation came from the bottom up, from sergeants and corporals finding better ways to do their jobs. The Bailey design was simple enough that practical improvements were obvious to the people actually assembling the bridges. This stood in stark contrast to German military bridges, which were complex enough that only engineering officers fully understood the designs. Enlisted German engineers followed instructions. They didn't innovate because the systems were too complicated for field modifications. By the spring of 1945, Allied engineering doctrine had evolved to treat bridging as a routine rather than a special operation. Planning documents assumed that any obstacle could be bridged within 12 hours, regardless of width or conditions. This assumption, which would have been absurd in 1939, was now conservative. Engineers routinely beat those timelines. The Rhine crossings demonstrated this evolved capability. When American forces reached the Rhine at multiple points in March 1945, the operational orders simply stated, "cross immediately." No detailed bridging plans were required, because commanders knew their engineers would handle any obstacle. Within days, 50 Bailey bridges spanned the Rhine at various points, carrying hundreds of thousands of tons of supplies and equipment. German forces attempting to defend the Rhine found themselves in an impossible situation. They couldn't prevent the crossings because Allied forces could bridge faster than Germans could respond. They couldn't destroy the bridges faster than they were being built. They couldn't even target specific bridges effectively because there were so many of them spread across such a wide front. General Oberst Gotthard Heinrici, commanding Army Group Vistula in the war's final weeks, explained the situation to his staff in April 1945. "The enemy builds bridges faster than we can destroy them, moves supplies faster than we can interdict them, and replaces losses faster than we can inflict them. This is not a military problem with a military solution. This is an industrial mismatch. They have converted their industrial capacity into combat power in ways we cannot counter. Every Bailey bridge is a symbol of that capacity. They don't build these bridges. They manufacture them like rifles or boots. We are fighting a factory, and we are losing to production rates, not tactics." This recognition that the war was being lost to industrial capacity rather than military prowess was devastating for German officers trained to believe in the superiority of German arms and tactics. Many had fought brilliantly, demonstrating tactical excellence and personal courage, but excellence couldn't overcome the fundamental arithmetic of production. For every bridge they destroyed, the Allies installed 3 more. For every delay they created, Allied engineers created 3 solutions. The final weeks of the war saw Bailey bridges advancing into Germany at rates that would have seemed impossible earlier in the war. Engineers were installing bridges across obstacles that German forces hadn't even finished demolishing. In some cases, Allied engineers were building Bailey bridges alongside German demolition teams, who were preparing bridges for destruction, the 2 groups occasionally in sight of each other across active front lines. In one remarkable incident near Leipzig in April 1945, German engineers finished demolishing a bridge over the Mulde River at dawn. By noon, American engineers had completed a Bailey bridge 300 yards downstream. The German engineers, observing from the eastern bank, reportedly made no attempt to shell the construction effort. One German officer later explained in captivity that they simply had no ammunition left and saw no point in wasting their limited supplies on a bridge that would be replaced within hours, even if destroyed. This resignation, this acceptance that bridging obstacles was futile, represented the complete psychological victory of the Bailey Bridge over German defensive doctrine. The Germans hadn't just lost the military capability to defend natural barriers, they'd lost the will to try because the effort had proven so consistently pointless. When German forces surrendered in May 1945, Allied engineers were operating hundreds of Bailey bridges throughout occupied Germany. These bridges remained in place for months and in some cases years, carrying occupation force traffic while permanent infrastructure was rebuilt. Many German civilians saw Bailey bridges daily, constant reminders of Allied industrial capacity and German defeat. In the post-war period, as Germany rebuilt, the contrast between Bailey bridges and German engineering tradition became a subject of reflection. German engineers studying the Bailey design appreciated its functional elegance but struggled with its philosophical implications. The bridge represented a worldview where good enough, deployed in quantity, beat perfect, deployed sparingly. This philosophical tension reflected broader questions about German technical culture. Germany had led the world in precision engineering, producing magnificently crafted machinery, weapons, and vehicles. But precision required time, skilled labour, and resources. Mass production required simplified designs, standardised components, and minimally trained labour. The Bailey Bridge proved that, in warfare, mass production won. The lessons extended beyond bridges to all aspects of military-industrial production. German tanks were superior to Allied tanks in many technical measures: armour thickness, gun power, engineering sophistication. But Germany produced about 50,000 tanks during the war, while America alone produced over 88,000. Soviet production exceeded 100,000. Quality couldn't overcome quantity when the quality gap was modest, but the quantity gap was overwhelming. The Bailey Bridge embodied this principle perfectly. Was it the best possible bridge design? No, German. Engineers could have designed something technically superior, but the best design was meaningless if it couldn't be produced in massive quantities, transported easily, installed quickly, and maintained by ordinary soldiers. The Bailey Bridge was the best design for the actual requirements of industrial warfare, which made it the best design period. Donald Bailey understood this instinctively. He wasn't trying to design the perfect bridge. He was trying to design a bridge that would work under combat conditions with the resources available. The rectangular panels, the simple pins, the modular construction, all of these features sacrificed theoretical optimization for practical reliability. Every design choice prioritized ease of manufacture and field assembly over technical sophistication. This approach required a humility that German engineering culture found difficult. German engineers took pride in solving problems comprehensively, creating optimal solutions that demonstrated technical mastery. Bailey's approach was to solve problems adequately, creating functional solutions that could be widely deployed. The German approach produced masterpieces. Bailey's approach won wars. In 1964, the British Army invited Bailey to observe a demonstration of modern military bridging equipment. New designs had been developed with improved materials and more sophisticated launching systems. Bailey watched quietly as engineers demonstrated bridges that could be deployed even faster than the original Bailey design. Afterward, Bailey was asked for his assessment. "They're very impressive," he said. "Much better than my original. But I notice they're all based on the same principles. Modular panels, simple connections, designs that can't be assembled incorrectly. That pleases me. The specific design doesn't matter much, the philosophy does. This statement captured Bailey's essential insight. He hadn't just designed a bridge, he'd established a design philosophy for military engineering equipment. The philosophy, that military equipment must be designed for the realities of combat rather than the ideals of engineering, proved more important than any specific design. Modern militaries have internalized this philosophy completely. Military equipment specifications now explicitly prioritize reliability, maintainability, and ease of use. Technical performance is important, but not at the expense of practical functionality. The Bailey Bridge taught this lesson so comprehensively that it now seems obvious, but it wasn't obvious in 1940 when Bailey started building models in his garden shed. The comparison with German military engineering remains instructive. Germany produced the V-2 rocket, the first ballistic missile, a technical marvel that demonstrated engineering brilliance. The V-2 required specialized fuel, launch facilities, and highly trained crews. Each missile took thousands of man-hours to produce. The V-2 killed approximately 2,700 people during the war, mostly British civilians. Britain produced the Bailey Bridge, a simple panel bridge that required no special facilities, minimal training, and could be mass-produced. Bailey bridges contributed to defeating German armies, shortening the war, and saving countless lives. The V-2 demonstrated what German engineering could achieve. The Bailey Bridge demonstrated what British engineering prioritized. The contrast in philosophy couldn't be sharper. Post-war analyses of military effectiveness consistently identified logistics and mobility as decisive factors in Allied victory. The Bailey Bridge appeared prominently in these analyses because it directly enabled operational mobility. Armies could advance as fast as their logistics could support them, and logistics depended on transportation infrastructure. The Bailey Bridge ensured that infrastructure could be established anywhere, anytime, under any conditions. German commanders recognized this in retrospect. Heinz Guderian, the architect of German armored warfare, wrote in his memoirs about the importance of logistics to military operations. He specifically mentioned the Bailey Bridge as an example of where German planning had failed. We focused on tactical mobility, ensuring our tanks could maneuver effectively on the battlefield. The Allies focused on operational mobility, ensuring their armies could advance across entire theatres. The Bailey Bridge was central to their operational mobility. We had nothing equivalent and paid the price in our inability to sustain defensive positions when natural obstacles could be crossed within hours. This admission from one of Germany's foremost military theorists validated Bailey's approach completely. Tactical excellence, which German forces demonstrated repeatedly, couldn't overcome operational disadvantages created by superior logistics. The Bailey Bridge created operational advantages that tactical skill couldn't counter. The economic dimension was equally significant. A Bailey Bridge cost approximately $1,000 in 1944, equivalent to perhaps $50,000 today. This bought a bridge that could carry 40-ton tanks across a 200-foot gap, be installed in less than a day, and remain functional for years. The cost per ton of cargo delivered across the bridge, when amortized over the bridge's usage, was negligible. German bridges, when they could be constructed at all, cost significantly more in materials and labour while providing less capability. The economic efficiency of the Bailey design meant that Britain could afford to build thousands of bridges, essentially treating them as consumable supplies rather than permanent investments. This economic approach to military engineering represented another philosophical shift that German planning hadn't anticipated. In the decades following World War II, military historians identified several technologies as decisive for Allied victory. Radar, which won the Battle of Britain, the atomic bomb, which ended the Pacific War, and the Bailey Bridge, which won the logistics war in Europe. Of these three, the Bailey Bridge was the only one that operated continuously from 1942 through 1945, affecting every campaign in every theatre. The bridge's influence extended beyond World War II into subsequent conflicts. In Korea, American engineers relied heavily on Bailey bridges to maintain supply lines across mountainous terrain. Chinese forces destroyed bridges systematically during their advances, expecting to delay UN forces. Instead, American engineers installed Bailey bridges that kept supplies flowing to frontline units. The same pattern that had defeated German forces in Europe defeated Chinese forces in Korea. In Vietnam, Bailey bridges supported logistics operations across rivers and ravines throughout Southeast Asia. The bridges proved resilient against monsoon flooding and enemy action. Viet Cong forces occasionally destroyed Bailey bridges, but American engineers reinstalled them routinely, often completing replacements before the enemy could withdraw from the attack. In the Gulf War of 1991, coalition engineers used modernized Bailey-type bridges to support the rapid advance across Iraq. The desert terrain, lacking natural obstacles, required fewer bridges than European campaigns, but the ability to bridge wadis and damaged infrastructure on demand contributed to maintaining the coalition's rapid operational tempo. The longevity of the Bailey design's influence, spanning from 1941 to modern conflicts, testifies to the fundamental soundness of its underlying principles. While materials have improved and specific designs have evolved, the core concept of modular, standardized, rapidly deployable military bridges remains unchanged. Bailey's insight into what military bridges actually needed to do, rather than what engineering theory suggested they should do, created a solution that has proven enduringly correct. In 2001, Donald Bailey died at age 94. His obituaries in British newspapers described him as the man who helped win World War II, though he'd spent most of his life as a quiet civil servant. The Times of London wrote, "Bailey's bridge was not the most glamorous weapon of the war, but it may have been the most important. It enabled Allied armies to go where German forces thought they couldn't go, arrive when Germans thought they couldn't arrive, and sustain operations that Germans thought impossible. In doing so, it made German defensive strategy obsolete and Allied offensive strategy unstoppable." The German perspective on Bailey's death was equally revealing. German military publications noted his passing with respect, acknowledging that his invention had helped defeat Germany, but praising the engineering insight it represented. One German military journal wrote, "Donald Bailey understood what German engineers did not, that perfection is the enemy of effectiveness. His simple bridge defeated our complex defensive systems not through superiority, but through adequacy deployed overwhelmingly. We should have learned from this during the war. We continue learning from it today." This acknowledgement that simplicity and mass production could defeat sophistication and precision represented a fundamental shift in German military thinking. Post-war German forces adopted American and British equipment philosophies, prioritizing reliability and ease of use. The Bundeswehr, when it was established in 1955, equipped itself with Bailey-type bridges rather than attempting to recreate pre-war German designs. This pragmatic choice represented the final victory of Bailey's philosophy over German engineering tradition. Today, at the site where German forces first encountered Bailey bridges in North Africa, at river crossings in Sicily, at countless locations throughout Europe, small markers note the historical significance of Allied engineering achievements. Some specifically mention the Bailey Bridge and its role in Allied victory. These markers are maintained by local communities who remember watching Bailey bridges appear, carrying Allied forces toward victory and liberation. In Burma, where British and Indian forces used Bailey bridges extensively during jungle campaigns, some bridges remain in place, converted to permanent structures by local communities who built permanent approaches and foundations under the original Bailey spans. These hybrid structures, combining wartime temporary bridges with post-war permanent construction, symbolize how Bailey's design transcended its military origins to become useful infrastructure. The Bailey Bridge's story is ultimately about the power of appropriate technology. It wasn't the most sophisticated bridge, the strongest bridge, or the most elegant bridge. It was the right bridge for the specific requirements of industrial warfare: mass-producible, rapidly deployable, operationally reliable, and tactically adequate. These qualities, which seemed almost mundane, proved decisive. German commanders who laughed at the Bailey Bridge in 1942, who mocked it as a crude, temporary structure unworthy of serious engineering consideration, stopped laughing by 1944. They stopped laughing when they realized that crude and temporary beat sophisticated and permanent if crude and temporary could be everywhere at once. They stopped laughing when rivers ceased to be barriers and defensive lines ceased to hold because obstacles could be bridged faster than they could be created. The laughter died when German engineers watched Bailey bridges span rivers overnight, carrying endless streams of Allied armour. It died when German infantry heard the distinctive sound of Allied tanks crossing Bailey bridges toward their positions. It died when German commanders realised their demolition efforts were futile because every destroyed bridge was replaced within hours. By May 1945, there were no German commanders left to laugh. The thunder had spoken in the form of 700 million feet of prefabricated steel, panels. The rivers belonged to whoever held Bailey bridges, and the Allies held thousands of them.